I think that's okay. Yeah. All right. Thanks, Ron. Appreciate it. Well, good afternoon, and my apologies for the technical problem. This course is about computational transport phenomena. So let me, before I start the lecture, I should just go over the Moodle webpage. I just activated it this morning, and you will find all the lectures posted there, except this one I'm just still struggling with. The recording part of it. So typically what I do is I record the lectures, and they are uploaded automatically to Moodle. And then I will upload after the fact the lecture notes. But I think I should also do it beforehand, so that if you want to look at it before you come to the class, that would be fine. And you don't have to take notes. What I would like, this is a graduate level elective course. And so the goal would be to kind of bridge theory and algorithms to literature to enable you to possibly use some of this in your thesis work. So it is about advanced computational modeling using computational fluid dynamics. And this is the Moodle web page, and you will see there the course outline, and then material, reading material. There are about 30 textbooks at the graduate level that I have put there. I'm not going to use any single textbook in this course. I will take material from different sources, and I will let you know as I take the sources from different places. And the course outline, the PDF file is there. Any assignments, any projects, I will upload also. On a week-by-week basis, the content that I upload will be organized in those. I guess all of you have used Moodle, right? So you're familiar with how Moodle works, right? So this is a place to come and retrieve the information on particular material. Now, in terms of the course evaluation assessment, I should say, what I plan to do is no exams. That should be good news to all of you. No, I shouldn't say that. No written exams. I'm going to focus more on thinking rather than problem solving, because very structured problems at the first level graduate course in transport phenomena in thermodynamics, you know how to solve them. But as you get to more complicated realistic problem that you will encounter in research or in workplace when you go to the job, so you will find the problems are much more complicated. You're going to build a project in this course. So about within a week's time, I will give you a list of 10 projects that I will suggest. But if you have your own project that you would like to propose that would help you in your thesis work, I'm willing to listen to that also. Okay, so we can assign, hopefully within the first 2 weeks, a project for each student. And the assessment will be based on, so this is the outline that I have uploaded, and these are all the textbooks that fairly advanced level, graduate level textbooks. There are about 34 books there. But this is the assessment part. So there will be some assignments. All assignments will be computational. So some could be involving COMSOL. I'm primarily going to focus on COMSOL and MATLAB as a solution tool for formulating problems and then for solving the problems. You are free to use other tools that if you have access to it in your own thesis work, OpenFOAM, Star CCM. If you want to learn an MD code, for example, whatever it is, the project that you propose. I would like us to focus on the continuum scale phenomena. So this course is about computational transport phenomena on the continuum scale. So the goal would be at the end of the course, you should be able to use some of this advanced software to look at diagnostics of processes, chemical processes, materials, minerals processing, petroleum recovery, whatever it is. using these advanced tools and to design some of these advanced tools. So the assignments will be to reinforce some of these algorithms using COMSOL and MATLAB. And they are worth about 25%, maybe 3-4 assignments like that during the course. And then the project work and report. Okay, that will be, the project report will be something like what you will see as you read papers. In each project I will give you 1 or 2 papers to start with, and then you will do the literature search to look at other papers in that particular area, and then write your own report in the same format as publication. So an abstract, an introduction, a literature search, and then problem formulation, and then reproducing some of the results in one of those papers maybe. Okay, using any tool, computational tool. And then there will be a presentation to class towards the last 2 lectures, 3 lectures or so, about 20 minutes each maximum. And then there will be an oral exam. That's where I think I kind of misled you. There will be an exam, but it will be an oral exam one-on-one. I will schedule a series of half an hour meetings with each one of you over a day or 2 towards the end during the exam period. And there I will explore mostly how much of the concept you have grabbed from the lectures as well as from working on your project. So questions would be both drawn from the project to see how much you understood about the project, as well as the modeling errors and the computational errors to get an idea of whether you have some understanding, so that when you're solving your own problem later on, you are using it in an intelligent fashion, using all these simulations in an intelligent fashion. So that's the overall framework in which the assessment will be done. Any questions? Yeah.
So how much pre-knowledge do you expect from like transport phenomena class or something? Because I haven't taken.
That's a good question. This is an advanced level course, right? So there is some expectation of not necessarily specific knowledge, but the ability to pick up the required knowledge as you need, particularly on your project, because 50 to 75% of the weight is on the project, right? So if you feel confident, and if you feel you have your own thesis project that you want to work along this, we need to engage in a discussion to see that I feel it is appropriate for the goals of what I've set for this course. Okay. Having said that, there will be some knowledge assumed from undergraduate level, differential equations, vector calculus, linear algebra, things like that. Okay, that's basic. That's what we will build on. Okay, but other than that, the concepts we will review, we will understand the averaging ideas and stuff like that we will go through. Okay, so I don't think that should be a problem unless a person comes from history and wants to take this course, right? Any engineering, any science undergraduate degree should be adequate to follow the arguments that we are making, I think. Okay, any other questions? Okay, so feel free to stop me and ask questions, and as I said, you don't have to take any notes or anything, because whatever you see in the class, I will upload it to Moodle. And from next time onwards, I will upload it even a day before so that you have access to them before you come to the class. These will be either a PDF file or PowerPoint files. And I will try to, if there are questions and that results in writing something, I will try to write it on the screen itself and capture them as well, so that you will also have a record of that. I can do that. Now, as I said, the course is about computational transport phenomena. So there are going to be 2 major important parts. One is transport phenomena. Okay, what is transport phenomena? It's essentially a phenomena that deals with transport of momentum, heat, and mass in a certain given environment. It could be a reactor, it could be flow through porous media in a reservoir, it could be atmospheric dispersion of pollutants, it could be dispersion of pollutant in the ocean. So that towards the end, I will give you some of our own research work in many of these areas and show how we have used the understanding of multi-phase flow to study some of these problems as a practical link to how you could use it in your own work. But the first lecture is going to be very general, philosophical in some sense, to try to set the big picture, the big agenda. Okay, so those are the pictures that you see that we want to understand how they are connected. Okay, so what are the major challenges facing humanity? Right. So it is essentially energy, and we need to harvest energy and use that in a most effective way so that it doesn't affect the environment. So global warming, for example, is a big issue. Why does global warming occur? It occurs because we are taking a lot of these, can you see anything there? Right, just give me the screen resolution problem is still lagging. Yeah, that's why when I write here, I put something there. Right. I write in one place, it writes in another place. All right. So I will today just go to the screen and show. So at this plane, essentially we are talking about using materials and energy, putting them through a set of conversion technologies to produce products that are useful to humanity. So here, fossil fuel is nothing but hydrocarbons harvested from sun's energy long time ago and stored underground. And the renewable energy is what the same process that is currently occurring. That is sun's energy captured in the form of hydrocarbons in plants. You can also capture sun's energy directly through solar cells, and you can also create energy through nuclear fusion or fission. In a sense, even these are nuclear energy coming from the sun, except the nuclear plant is far away, but in this case, the nuclear plant is on Earth and we are controlling it. And there is a whole cycle that we will talk about later on, but process innovation is about trying to come up with new process designs, understanding the multi-phase flow phenomenon that occurs in these vessels. So any chemical plant, there are over 300 plants in Louisiana along the Mississippi River. Any plant essentially does one of these three things from a chemical engineering point of view. Either we separate mixtures that are mixed, we mix mixtures that are separated, and we react them. Separation, mixing, and reaction are the fundamental core, often in a multi-phase environment, in a catalytic reactor, in a vapor-liquid contactor, in a packed column absorber, etc. Liquid-liquid extraction to immiscible liquids. So multi-phase flow is either gas-liquid or gas-solid or liquid-solid or gas-liquid-solid, where more than one phase interacts with each other, being transported by applied forces. So that's something that we need to understand. And exchanging heat as the heat of reaction, for example, or removing heat in a heat exchanger, and exchanging mass, because we want to transport the species from one point to another point, bring two molecules close together so that they can react to form a new product. Okay? And in process intensification, the goal is to give every molecule the same experience as it flows through these complex equipment. Okay? So how do we understand the heterogeneities that spontaneously form in such vessels, and how do we redesign them for future generations such that we take control of the homogeneity in flow? So transport phenomena is then about understanding these processes of heat and mass transfer coupled with fluid mechanics, coupled with chemical reaction. That part we call multi-physics. When there is more than one physics, in the sense heat transfer is a physics, mass transfer is governed by a certain physics, and reaction engineering is governed by a certain physics, turbulence is governed by a certain physics. So when all these things happen, we call that framework as a multi-physics framework. And packages like COMSOL are able to handle complicated multi-physics model equations to solve them simultaneously, to look at the interaction between these. And the other phenomena, the other terminology that we would come across is multi-scale. What does multi-scale mean? It essentially means phenomena that occurs all the way from molecular scale to the equipment scale that you see here. Large 20 feet diameter distillation column, for example. So the course is about formulating these models, understanding the approximations invoked in those models, and trying to relax those as much as possible to get as rigorous as possible in our design equations. When we do that, we will find that the equations that we end up with are very, very complicated. And so computational way is the only way to solve these. And this is why it is computational transport phenomena. So this is a highly condensed picture. This is a picture that I learned when I was a graduate student from my supervisor, and I like it very much. So it essentially tries to relate the physical model with the mathematical model and the computational model to show you the link and the various types of classifications. Again, don't take notes of these things. These will be put up. So let's start with the top one. Okay, the physical world. The physical world is anything that we are interested in, right? For a physicist, it will be the planetary motions, maybe the trajectories of the planets and the moon, etc. For a chemist, it is the chemical reactions between two reactants. For chemical engineers, it's chemical plants. For petroleum engineers, it's a reservoir, maybe, or the surface facilities for separating the gas and oil, etc. So any natural process that we are interested in studying, we observe. We observe, and that is the empirical observation, and we collect data. Okay? This has happened for centuries and centuries with data on the astronomical observations, as an example. Data on the physical observation, Charles Darwin's theory of evolution, for example. And conceptual modeling is one where we just do thought experiments. Okay? Einstein's example for relativity of two observers in a train watching how the light travels, for example. So we can do a combination of these thought experiments, physical observations, to understand conceptually what the phenomena that we are interested in about the physical world. And in some cases, we want to build a mathematical approximation of the physical world. The reason that we want to build a mathematical approximation is, why would we want to build a mathematical model? Any ideas? To predict. That's the key, right? Now, you can predict by simply tabulating the data, looking at the data if the data occurs in a repetitive manner. And there are a lot of new powerful tools that are coming out with deep learning and data-enabled learning and prediction. But in the early stages of model building, it was essentially building a mathematical model. So we had to develop the apparatus to do that, meaning we had to invent geometry, we had to invent algebra. It didn't exist before, right? We had to invent calculus, right? All these provided as the framework for expressing those concepts in terms of mathematical equations. And those mathematical equations often are highly nonlinear and very complicated. In very few cases, you can solve them analytically. And so computers have enabled our ability to probe these natural phenomena by solving these mathematical model equations in a very rigorous manner. Okay? So from the physical world, through the conceptual modeling or the empirical model that you see there, you build a mathematical approximation. So this is an approximation to the physical model. Okay? And there are several classifications of these physical models. Okay? So on the left side, you see classification of linear and nonlinear models. But as I said, linear models are very rare in Earth. And so the nonlinear models are the more realistic models in terms of describing the physics. The other type of classification would be steady state model versus dynamic models. Now, I know the spread or the dispersion in a class like this is going to be likely large, meaning different people will have different experience. So if I throw a term that doesn't make sense, please don't hesitate to put up your hand and ask so that I can explain, I can give you examples of those. Okay? So steady state models are ones that don't change with time. Dynamic models are ones that are changing with time. And those models can be linear or nonlinear, but they have additional attributes of whether they are changing with time or invariant with time. Then within that, you have the classification of lumped or distributed models. Lumped models typically have no spatial variation of a quantity that you are observing. Okay, it could be a velocity, it could be temperature, it could be concentration. We're saying that these variables vary only with time, but not with temperature. If you sample at two different locations, the velocities will be the same, or the temperature will be the same. If we make that assumption, under certain conditions, those assumptions are fine, then you'll end up with lumped model. But if those variations are significant, then you end up with distributed models, okay? Distributed spatially in all the three dimensions. And they again give rise to different types of model equations. Okay, the mathematical model equations can be algebraic, can be differential equations that evolve in time, can be differential equations that evolve in space, it can be partial differential equations. So each type of model will require us to use a certain type of numerical methods to solve them. This is why we need to understand the classification of the model so that we can pick the right type of numerical tool. And COMSOL and MATLAB have a number of these tools built in. So we will learn how many of you have not used MATLAB? 1, 2. How about COMSOL? More. Okay. So we will have a demonstration in the class as we go along. I'll give you examples, a demo, and those are also being recorded, so you'll be able to play with it. But that's a part that we will try to reinforce to bring homogeneity in the entire class through assignments. Okay, I'll give you assignments that are not very complicated, but illustrate some simple ideas using MATLAB or using COMSOL after I demonstrate how to solve such classes of problems. But MATLAB and COMSOL live in this space. Those are numerical way of solving the mathematical model. And different tools are available, so you need to have an understanding of these classifications to be able to choose the right tool to solve that problem, either in COMSOL or in MATLAB. Okay? So the mathematical model is an approximation to the physical world, and the numerical model is an approximation to the mathematical world. So there are errors in both places, and we need to understand what are the errors introduced in building the mathematical model to represent the physical world, and what are the errors introduced in the numerical model to represent the mathematical model. So the second link, the errors between the mathematical and the numerical model, are called numerical errors, truncation errors. There are errors introduced by the numerical scheme that we will build. And that's an important part of this course, to understand the origin, the sources of those errors. And the sources of errors in the first one, from the physical model to the mathematical model, are essentially the approximations that we make in saying that I'm going to ignore spatial variations, for example, in temperature or concentration. I'm going to assume homogeneity, which may not be true in reality. So modeling errors coming from that. So we need to understand what are the origin and how we can manage those errors as well. Okay? Any questions? How many of you feel you're lost? I hope you're not, but I just need to sense the level. So these terminologies are okay for you, right? Lumped versus distributed, steady, dynamic, etc. Okay. So this is now getting into trying to understand the problem. I have several pictures here, and let me talk briefly about innovation and invention. Okay, invention is something that you build that doesn't exist before. This was a definition or classification that CTO, the Chief Technology Officer of Dow Chemicals, proposed. I think there is a YouTube video that he talks about difference between invention and innovation. So you see on the left a Model T, an old car produced in 1904, right? On the right you see a modern Porsche, which is a high-performance car, right? And this, from here to here, we went through sustained innovation. Innovation that is cutting 5% energy improvement per year, 2% in drag reduction here. So through design innovations, we go from a Model T to a modern Porsche in the automotive industry. And so innovation then is incremental sustained improvement that leads to a large improvement over a period of time because of the sustained nature of it. Here is a Wright Brothers plane, here is a modern Dreamliner, and again the performance improvement over a 100-year period have been phenomenal. This is achieved through sustained incremental improvement using design tools that are becoming more and more sophisticated. So this course is about understanding those tools, computational tools. Computational models are used very heavily in both design of automotive and aeronautical in planes. For example, today you can build a plane using CFD without ever putting the design into a wind tunnel experiment. Are you familiar with what a wind tunnel experiment is? So previously, when you were designing a plane, you would put it in a wind tunnel, test it to make sure that it has the right drag and the right lift, etc., to make sure that the plane is stable, that it will actually fly. But today we can do that with just CFD. Aerodynamics is so advanced models are adequate. We can build, we can have confidence in them to build and to optimize the design of planes. This is a room full of computers called ENIAC that was built in the 1940s for some neutron diffusion calculations, I think. Those are all based on diodes, so a room full of like this, but that could do only maybe 100, 200 floating point operations per second. And this is a computer that you hold in your hands. Everybody has that. A cell phone that can do millions of floating point operations per second, and it is a million times smaller. Again, a phenomenal improvement in performance and in energy consumption, in size, in the number of floating point operations. So this is what enables computational tools to be used to design these things. And if you ask a question, what happens in the chemical industry, in the petrochemical industry, etc., this is a distillation column in the 1940s, and this is a more modern distillation column, right? How many of you are from outside of chemical engineering? Okay, so I will tend to use chemical engineering examples because that's what I'm familiar with. But if you have questions about those examples, please feel free to ask. Or if you want to offer other examples from your own domain, we can also talk about them and discuss that. Okay, so if you ask a question, what is the status of innovation in chemical process design, chemical equipment design? The answer is very little. So this is what the inside a distillation column looks like. Okay? So you have a liquid that is coming down, flows across over a tray, and there is a weir there, and it flows over that to the next tray and down. So these are stacked, 50 stages, 60 stages like that. And the goal is to separate two species, methanol water, for example, and ethanol water from corn, for example. So you would set up a temperature gradient in such a way that the bottom part of the section is hotter than the top part. So the more volatile material will be evaporated and go towards the top, and the less volatile material will go towards the bottom. So you achieve separation using a principle from thermodynamics on volatility differences. Okay? Similar things can be designed for absorption, for extraction, etc., using different property differences to separate two species. Now, this is a multi-phase situation. What happens here, there's a pool of liquid, and there's a vapor that comes through these sieves, and then they bubble through it. And each phase, there's a liquid phase and a vapor phase. Each phase carries at least two different species, two different components. Okay? Methanol water as an example. So as they mix, what would happen is the methanol from the liquid should go into the vapor, and the water from the vapor should go into the liquid. So there is mass transfer. There is mass transport, and there is drag between the bubbles and the liquid. And they mix vigorously, and then they separate. Okay, in this zone, the two phases separate, and the vapor goes up along its path, and the liquid will flow down. Okay? Now, what you see in these images are internal flow structures. Okay? As the vapor rate is increased from left to right. So this is on a single tray. And these videos are again available in YouTube, put out by a company called Fractionation Research Incorporated. Okay? So in the leftmost figure, if I can get the animation to work again, maybe you need to go back and come back. Yeah. So here the vapor rate going up is so low that the liquid from the tray above drips. And this is called the weeping regime. Okay? When a liquid from the top, it should go down only through what is called a downcomer. If it drips like this, it's actually mixing. We want to achieve separation, but it is mixing. In the other extreme, when the vapor flow rate is so high, it atomizes all the liquid. It's very fine spray, and the liquid droplets are carried to the tray above. That's called entrainment. Okay? And that also results in mixing. You want to separate, but in both extremes, low flow rate and high flow rate, you end up mixing them. The fluid mechanics in this one is very complicated to study because there are literally millions and millions of droplets and millions of bubbles. In here is the ideal regime where you have what is called a nice froth regime. And okay, so you can see how dynamic it is. And you can see how spatially heterogeneous it is. The velocity here is not the same as the velocity here. So to describe such a phenomena, we need complicated partial differential equations because things change with space and things change with time. Okay? But that's an ideal regime to operate because there is vigorous mixing between the vapor and the liquid. In the bottom portion of the zone, there is a disengagement zone where the vapor and liquid completely separate, the vapor goes up. And ideally, a column should operate in that regime. So to understand and to design these columns is a very challenging task. And still we invoke a lot of approximations. And we need to understand the sources of these approximations and errors in modeling. Any questions on that? Particularly those that are not chemical engineers. Do you understand or get an idea of how complex the process is? Okay, so we are trying to understand the vapor-liquid interaction and to control it and design it such that it always operates in this regime. But we are literally dealing with millions and millions of bubbles and droplets. Yeah.
It might not be related, but is there any case that we have all these phenomena in a specific column? Like, for example, in the beginning, at lower stages, we have, I don't know, spray.
Yeah.
Or spray, and at the top we have whipping, and in the middle we have our ideal froth phenomena.
That can happen. In a poorly designed column, these things can happen because it depends on how much of, how you control the temperature along the column, right? If there is a lot of heat loss, this is a 50 feet column and there is a wind blowing on the top and you haven't insulated it. So you want to condense only a certain amount of liquid and return it back. But if there are additional amount that condenses because it is exposed to cold temperature. So between winter and summer, you can have a different performance of the column, right? So those things are all possible. And as engineers, what we need to develop is develop these clues. Like if you have the logic, you can then say, this might be happening. So I can do a simulation of heat loss when cold air is blowing across such a column. In Edmonton, that's where I was, in Canada, where the temperature can drop down to minus 30 degrees. And they still operate these refineries under those conditions, right? So all these things can interact and create poor performance of the column. Even though it is well designed to operate under ideal conditions, it may not. Yeah. So these are pictorial representations of the so-called various regimes, the froth regime, the bubble regime, the spray regime, the foam regime, for example. And how do we design these? We've been distilling, I guess, spirits and wines for a very long time, 2,000 years. We've been building and experimentally playing with it to find out how to optimize these things. So that kind of experimental data is then captured in a diagram like this. This is called a flow regime map. And what you're plotting here is the liquid flow rate versus the vapor flow rate. And if the liquid flow rate and vapor flow rate are somewhere in here, you get a froth regime. So you continuously change, for example, for a given vapor rate, change the liquid rate, and see when the flow pattern changes. These are observed in an experiment. These are called pilot scale experiments. And then you draw the boundary. Right? So you draw these maps, the boundaries for these various flow regimes, and they become operators' guide in terms of deciding how far can I increase the liquid flow rate, for example, or the gas flow rate. Often those are determined by the quality of the crude that you get, the need for producing a certain types of fuel, gasoline or diesel or heating fuel in different parts of the season. So you need some variability, ability to change your operating conditions in a plant And this sets the boundaries. If you cross these boundaries, it cannot work. Now, if you ask the question, can I predict these boundaries without doing experiments? And the answer to that is still, it's a challenge. The simulation tools have not progressed to a level where you can actually predict these boundaries. If you ask the other question, how invariant are these boundaries? So suppose I do this measurement in a 6-inch diameter column in a laboratory. Can I use the same diagram in a 6 feet diameter column in a plant? And the answer is no. They change. They change if you change the physical property. They change if you change the diameter of the column. And that's one of the challenges in multi-phase flow. The changes in the flow pattern can occur, and they are very sensitively dependent on the geometrical dimensions, the fluid properties, etc. I have a few examples of other results that will show this. So here is an example of in a pipe flow. Okay, so you have a horizontal flow, and this is a very common problem. There are literally millions and millions of miles of pipes in North America carrying crude, carrying natural gas mixtures from the production field to the processing plant, and then on to the distribution to the homes, for example, where we get natural gas by pipelines, right? So depending again on ambient temperatures and pressures, the natural gas may condense, produce some kind of condensates, depending on the composition and mixture. So thermodynamics plays a role with fluid mechanics, with multi-phase fluid mechanics, to determine the dynamics of how the flow patterns can be. So here, for example, the top one is called a segregated flow. Okay, so your top part of the thing carries the gas, the bottom part carries the liquid. So the velocity is not very high. So gravity pulls the heavy material, and the liquid is at the bottom. Now, as you increase your pressure, as you increase your velocities, you will find that the interface begins to form waves. And these waves grow in size, and they go and touch the top, and then you form slugs. Okay? And if you increase very high velocity, then the liquid is completely atomized, and you have droplets that are moving in the core with a liquid film on the side. So once again, as you change the gas-liquid ratio, it goes through various patterns: stratified flow, wavy flow, bubbly flow, slug flow, etc. Once again, we need to have a map to identify where the regime changes are. And those maps are dependent on, this is for air water system. If you put a different natural gas liquid system, the map would be different. Okay, and if you measure this in a 3-inch pipe diameter to measure the pressure drop, that's what, as an engineer, we are interested in, flow rate versus pressure drop relationship. You cannot use that map to design a 36-inch pipe diameter because the flow patterns will change, the boundaries will move around. Right? The same thing happens with a vertical flow, a flow in a vertical pipe. And traditionally, the engineer's approach is to express all these quantities in dimensionless forms. So we introduce Reynolds number, Froude number, Weber number, etc. In the hope that when we express them in dimensionless form, because these are ratios of forces in a dimensionless setting, as long as these ratios are the same, whether I have Reynolds number of 2500 in a 1-inch pipe or a 12-inch pipe, if the Reynolds number is 2100, one would expect the same kind of a flow behavior, right? That happens in single-phase flow, but not in multi-phase flow, because that regime may be completely different. Okay, even though you have kept the Reynolds number, there are other numbers that have to be kept same true, like Froude number. Froude number is inertia to gravity, and Weber number, it's viscous to surface tension forces. To keep the ratio of all these forces concurrently, simultaneously the same as you scale up is a challenge. And petroleum engineers, I'm sure you face this whenever you build, for example, what you call a scaled physical model of a reservoir, right? You know that you cannot scale everything about the reservoir down to that small laboratory scale. Okay, the reservoirs are spread on miles and miles, and your setup may be meters, right? And so you cannot preserve all these dimensionless ratios. So dimensionless, expressing them in dimensionless numbers and developing dimensionless maps helps to some extent, but it is not the solution. What is the solution? A rigorous model that captures the interaction between the phases on the dispersed phase scale, on the size of the droplet, on the size of the bubble. If we can develop models that capture these interactions on those sizes, then the large-scale structures can be captured through using the advection mechanism, right? And that's what this whole course is going to be about. How do you capture in the modeling part, not in the computational part, but the modeling part, how do you understand and capture these interactions, the drag, the lift interactions, etc., on the dispersed phase scale in a way that's rigorous, that's fundamental. Okay, any questions? Okay, so here is another graph that I've taken from a paper by Andretti, and he has a nice book called The Physics of Gas-Liquid Flows. There are books, entire books devoted to gas-liquid flows, gas-solid flows, liquid-solid flows, etc. So it's a vast subject. And if you take the theory manual of COMSOL or ANSYS, they are 800 pages, 900 pages long. They just summarize all the equations. They don't tell you how they are derived, what are the assumptions, what are the limitations, etc. Even to go over all those equations would take a whole course, right? So we are not going to do that. We are going to take the equations that we need to discuss the general ideas. And once you get the basic idea of how to approach a problem, then you should be able to take these model equations from COMSOL for any problem, electromagnetic, solid mechanics, whatever it is. This one was taken by Andretti, and it essentially shows how sensitive are the boundaries to changes in the diameter. So you go from 2.54 to 9.53 centimeters. Okay? You increase the diameter of the pipe from 1 inch to maybe 3 inches or so, you'll find that the boundaries of these flow regimes change. And as I said, this is still a problem. This is experimentally determined every time. There are some inroads being made to predict from a direct numerical simulation, so-called DNS. And so as we go along in this course, you'll also get an idea of unsolved problems, challenges that are in the general area of multiphase flow. So this is the same thing for a vertical pipe, gas-liquid flow in a vertical pipe. And what you see here is a change, and this change is important to understand when you're modeling, even in a kind of an average sense that we'll talk about later. But what is the change? In a bubbly flow, what is the continuous phase? Liquid, because it's bubbles. The dots that you see are actually representing bubbles. Okay, bubbly flow is one where liquid is continuous and you're bubbling gas through it. I think you have a nice experiment. If anybody wants to see a bubble column, go to his lab. Size has a nice lab where we have built a bubble column. Okay, and as you excuse me, as you increase the gas flow rate, these gas bubbles come together and coalesce, and they can form big slugs like this. There's a big gas, and then there's liquid. But as you continue to change this, what you find is, here it's a dispersed flow. And what happens here is, gas is the continuous liquid. The gas flow rate is high, the velocity is high, the volume fraction is high, liquid is present in a smaller amount, and so the liquid is basically broken down into droplets. So here the direct interaction is between the continuous and the dispersed phase, with liquid as a continuous phase. Okay? Here it is the gas as the continuous phase. And if you have done a transport phenomena course of drag on a single sphere, you will know that the drag depends on the properties of the fluid, the density, viscosity of the fluid, and the dimensions of the particle itself. So you need to be able to build models that will make this transition in accounting for the interaction in a correct manner. So by looking at a few examples from distillation and pipe flow, what have you learned so far in a conceptual framework? That the spatial variation of phase distribution, by that I mean what fraction of a liquid is in a certain region of your equipment, what fraction is in the form of a gas. It's hardly homogeneous. But every model that we build, from CSTR, a continuously stir tank reactor, in Darcy's law, for example, in porous media, you assume it's essentially a plug flow, right? So we assume homogeneity, but nature is hardly homogeneous when it's dealing with multiphase flow. The other thing, this is a statement I'm making, but I think we need to kind of demonstrate that as we go along. That is, to predict the macroscopic performance. By that, what do I mean? What is the macroscopic variable that we are interested in the design? If it's a pipeline, I would like to know what is the capacity of the pump to pump a certain amount of gas-liquid mixture, right? So it is the relationship between the flow rate and the pressure drop that I'm interested in a pipeline. In a distillation column, what am I interested in? How much of species methanol I can transfer from one phase to the other phase. Okay? So to know that, I don't need to know where every droplet or where every bubble is, because there are literally millions of them, billions of them, right? So I need to kind of develop a scheme where I smooth out, filter out information on the dispersed phase scale, but capture that information in the form of what we call a closure relationship. We will understand what it is later on more precisely. So that's where we introduce this concept of so-called interpenetrating continua, and I will illustrate through a figure what that interpenetrating continua is. From our experience so far, the same class of so-called closure models seem to be adequate for same class of problems. Okay, but if you change the class of problems, change the flow patterns, then the closure relationships would have to change to represent that interaction. As I've said before, it is still difficult to predict the flow regime transitions from one regime to the other regime. So getting back to the distillation column example, here you see a single tray. And what you see here is, this is the region where the liquid will come down, and this is the region where there are thousands of tiny holes, and the liquid will flow across. There is a weir here, and that will maintain the pool of liquid, and it will flow over that. This is called the downcomer. Okay? To assume that the velocity of the liquid here and there, or the velocity of the gas, is the same is not correct. But McCabe-Thiele method, Aspen type of simulators use that kind of an assumption. And that's an assumption that leads to modeling error that we need to take control of. Okay? And people have measured, for example, what is the velocity variation across the diameter of the column experimentally. And I have some results I will show you that. So our goal is to then see whether we can predict this vapor liquid flow across such a tray. And you see this is about probably 20 feet diameter. You can see the scale with respect to the man that's standing there. The secret to that is all contained in this equation. Anybody recognize what that equation is? Pardon me? Conservation equation. That is a momentum conservation equation. This is the mass conservation equation. So it's a combination of both mass and momentum conservation. So this is mass times the rate of change of velocity, which is acceleration. Some of the external forces. Gravity is the force, and then the so-called viscous forces, right? So this is nothing but Newton's law of motion. This is conservation of mass. Navier-Stokes equation, if I replace this with Newton's law of viscosity. Okay, otherwise this will be called the stress equation of motion. Now, when you see this and you haven't seen this before, how many of you are uncomfortable? All the software tool like COMSOL will solve these equations. Okay, so when we do an example in COMSOL, you will see the exact form of the equation. Okay, but there are lots of challenges in solving these equations. In fact, I should point out, at this stage, we have written down the equation. Okay, that is coming from Newton's law of motion. It's called the Navier-Stokes equation. We don't even know whether a solution to that equation exists. So a mathematician worries about those things, right? If you write down the equation, he would ask, is there a solution to that equation, right? And if you can prove that a solution exists, you get $1 million prize. There is a $1 million prize awarded to that question, answering that question, whether Navier-Stokes equation, do solutions exist, so-called existence problem. But pragmatic chemical engineers, or engineers, mechanical, this is used by chemical engineers, civil engineers, mechanical engineers, aeronautical engineers, marine, shipbuilding and design, wherever there is fluid. Think about it. The two of the most abundant fluids on this planet are air and water, right? So we are kind of soaked in the fluids. We are interacting with these fluids all the time. And so obviously fluid mechanics is of interest to everybody, but it is one of the most difficult subjects in petroleum engineering, in chemical engineering. So we push it under the carpet and say everything is nice and homogeneous, and we make these simplifying assumptions in our design methodologies that we develop. Okay? So those fields where they have addressed this head on, particularly in automotive and aeronautical engineering, they have made greater strides in their design innovation. And in petroleum and in chemical and mineral processing, where we don't look at fluid mechanics as an important subject, we are paying the price in terms of very long time to develop a new technology because we have to do it through pilot scale experiment, etc. So the only way to access the solution to these, except for some trivial cases, is through computational means. And that's why it's called the computational fluid dynamics. If you solve these two sets of equations, it is CFD, computational fluid dynamics. If you solve these two equations together with the mass conservation for a species or the energy conservation with the reaction, etc., then you have a computational transfer phenomena in a sense. Now, the Navier-Stokes equation is valid on all the scales, from the continuum scale to the equivalent scale. But we cannot compute such complex multi-phase flows. In principle, the secret is hidden there. But the only scale over which this will fail is when you go into molecular scale. So if you have a catalyst particle, for example, and molecules are diffusing through the tiny pores, and the pores are nanometer in size, same size as molecules, then this framework will drop down, will fail. But as long as your scales are large enough to include, say, 10,000 molecules or so, you can smooth them, you can smear them, you can treat that point as a continuum point. Okay, so you're talking about average velocities of many molecules. So this is with apologies to non-chemical engineers, this is a point to drive the kinds of approximations that we make in our design procedure. This is how we design a distillation column. There's something called the McKay-Thiel method. Two professors from MIT developed this in the 1925. You can imagine how late we are. We've been distilling things for 2,000 years, but by purely empirical means, trial and error method. Right? But these two guys put together a framework for actually trying to identify how many stages there are needed. So essentially you're plotting composition in the vapor phase against the liquid phase, and this is the equilibrium information that comes from thermodynamics, and these are called operating lines that comes from the liquid and vapor flow rates, and each one is a stage. So in a stage you can release the composition only by that much, in another stage by that much. So you count and say, okay, I want a 99% purity here and 0.01 purity there. You can count the number of stages and design your column. And because you're making these assumptions, so-called constant molar overflow and well-mixed stage, you don't trust the result that comes out of it. So if it says that I need 25 stages, you'll probably put 35 stages just to make sure that you're going to achieve the separation because of the uncertainties in the model coming from these two assumptions. Now, this assumption has been removed with the introduction of process simulators like Aspen and ISIS, because you can handle varying flow rate from tray to tray. Okay, because of the things that we talked about, cooling and such and increases the liquid flow rate, for example. So the operating lines need not be straight lines anymore as represented by this mass balance equation. It can be actually a curved one, but you cannot solve it analytically, you cannot solve it graphically. You need to use a computer for that. Aspen and ISIS will do that. This assumption hasn't been removed in Aspen. So Aspen still assumes the tray is well mixed. The composition is the same everywhere. Okay, to address that, they build into the model a fudge factor, so-called tray efficiency that you can put in. But there is no way to predict the tray efficiency. You need to measure that from experiments. So CFD can help handle this, removing this assumption of well-mixed stage, because we know that it is not well-mixed. Okay? So we took this as a project about 10 years ago through a master's thesis in the previous place that I was working on. So I asked Gautier to just set up a simulation for a single tray. Okay? So this is the geometry that he built. So here is an entrance for the liquid. It enters like this. It flows across. There is a weir. It will flow over that. And these are the holes through which vapor will come in. And you'll have vapor-liquid interaction between these two. So we use something called a two-fluid model to model the hydrodynamics of this. And what you will see here is a simulation that produces. So by the end of the course, you should be able to produce results like this for a given problem on a project that you have. Okay? To be able to map out the spatial variations in the volume fraction. In this case, red means liquid volume fraction is 1, white means the vapor volume fraction is 1. Any other color in between maps between 0 and 1. So you can see that near the holes, the vapor volume fraction is high. In between the holes, the liquid volume fraction is high. Right? And what changes here is the liquid flow rate and the vapor flow rate. So he did it for several different situations. This was published in ASEHE. But this is, some people would just call it as CFD, colorful fluid dynamics, because we produce pretty colorful pictures. But are they real? How do they quantitatively agree? That's an answer that we need to seek. So we looked for a paper. This is the animation of how the path of a vapor stream will be, and what is the path of a liquid stream will be. And here you have liquid that is accumulating here. You can see it's flowing over the vapor. Right? So it looks qualitatively correct, okay, but quantitatively, how does it compare? So there was a paper that was published by Solari and Bell in 1986, and they used, this is important for us to understand because it tells you about what kind of measurements we need to make. Okay? So this is the grid that they used on a distillation column with just air-water flow. Okay, so they have water flowing down and air bubbling through that. And they built a device with fiber optic probe. Okay, so essentially they shine a light, and the reflected light gives you a measure of what fraction is liquid, what fraction is vapor. And it also gives you an idea. They put this in different locations, for example, at 4 and 8. Then they put a tracer, and they see when this tracer passes that point 4. And then when this tracer passes point 8. So by the time it takes to travel from here to here, they know the distance. If they know the time that is given by this detector, you can calculate what the velocity is between these 2 points. That's an average velocity, because at every point the velocity may be changing as it goes from 4 to 8. But with this measurement resolution from 0.057 to 0.209 over 0.15 centimeters or so, you get an average velocity. So the question that we need to understand, the more deeper question that we need to understand is, what are we measuring? Over what scales? Is it average? For example, if I give you a pitot tube and say, go and measure the velocity profile in a circular pipe, right? So the pipe is something like this, and a pitot tube. You know what a pitot tube is? It's essentially a tube like this, and if the liquid is flowing like this, you point it in this direction. So the kinetic energy is converted into pressure energy. So you get a pressure signal with a manometer there, right? By attaching to this, for example. So from that, you can calculate what the velocity is at a particular point. When you move this across, then you can actually get the velocity profile. It looks something like this. Okay? That instrument gives you the velocity at a particular point. But how big is that point? It depends on the size of the opening in the pitot tube. So it gives you an average velocity averaged over that size. Okay? But I can also measure the velocity by putting, what do you call this? Orifice plate. What does the orifice plate do? It creates a pressure gradient in the same tube. By putting a manometer across this, you can measure what the pressure variation would be and convert that into a flow rate. That gives you an average flow rate over the entire cross-sectional area, because it gives you only average velocity. Okay? Whereas this gives you point velocity. Right? So when we are predicting something, what are we predicting? Is it the average velocity or a point velocity? That's something that we need to worry about, because when you're talking about a point, when there are two faces that are going, how big is that point? Right? Maybe a point is so small that at some instances only gas is present, at other instances only liquid is present. Right? So what instrument are we using to detect information about the gas and the liquid, or the solid and the liquid, etc.? And over what scale are we smoothing out, averaging out? So in this particular case, they gave us exactly 4 data points across the diameter. And so this is a quantitative comparison. The student went on to compare the velocity along the diameter of the tube. So the velocity was not plug flow. It was changing quite dramatically. And the three curves that you see are from the CFD simulation for a two-phase mixture. We'll talk about what model exactly later on. I'm just trying to lay the landscape for you for types of challenges and the type of questions that you should pose and see what kind of answers we can get from that. Right? So that's an encouraging result, that these models are adequate to predict the velocity variation, including the variation here. I guess the zero line is here. So if you extrapolate it all the way, that shows that there are some negative velocities. Imagine if you have a curved surface, near the end, it's possible that you have reverse flows. Okay? And that's being captured in that simulation. So we have been talking about the types of challenges, using distillation as an example, how one can go about answering some of those questions without any detail. But as I pointed out earlier, multi-phase flow is very common in nature, very common in process industries. And these are several examples. This is the sand dune formation. There are very beautiful patterns that form. Why do they form? It's an interaction between wind and sand, right? And same thing would happen in sediment transport in rivers, right? So there are situations, and avalanches, for example, are also multi-phase flows. Emissions of volcanic eruptions are multi-phase flows. And those are all multi-phase flows that occur in nature. Here is another one that occurs in nature, deposits in artillery, for example. And these are in petroleum engineering, right? In the drilling, removal of the cuttings with the drilling mud. Okay, so you can assume the drilling mud to be a single phase, but you have solids that are being transported in that. And this is a propellant in a fracking situation where it goes into the fractures. And this is a FCC unit that's used typically in refineries, for example. Grain silos. So there are lots of examples where you have gas solid, liquid solid, gas liquid systems. And can we develop a common framework, at least a few sets of models that can be applied to understand all of these phenomena? So here I'm pointing out some of the more controlled experiments that people have done with multi-phase systems for the purpose of validating these models. Okay? This was done actually by a PhD student who just graduated from our department. And the problem that the guy who did the experiment, these are the experimental results, was the following. He took glass beads, made a suspension in glycerin, put the glass beads, these are tiny 300 micron size glass particles in glycerin. And then he had a jar of pure glycerin. And into that, he will make a blob of this suspension of glass beads in glycerin. Imagine now, if I just take one glass particle and leave it in that glycerin jar, what would happen to that glass bead? It will sink, it will settle, right? Why? Because of the forces acting on it. So there is weight, gravity is pulling it, and then there is of course buoyancy because it is submerged in a liquid, and it reaches the terminal settling velocity. There is a drag the liquid exerts on the particle as it moves, and these three are in balance, so it reaches the terminal settling velocity. This was known very long time ago, Stokes solution, right, to the Navier-Stokes equation. But the question that these guys are addressing is, would that blob with thousands of particles, not just one particle, how does it behave? Does it behave like a single particle? Does it settle faster? What would you expect if you are doing this experiment yourself? It will settle faster, and it might lead to a trail of beads, which you see in the simulation and you see in the experiment. But it also does a lot of other things, funny things, right? And that's why this problem is fascinating. It will be a good project. It will be a good project. Variations on this would be fantastic projects for you. So what happens here is, at very low Reynolds number, it behaves like a effective larger sphere. Okay, so there is an internal circulation. So it behaves like a liquid. So there is an internal circulation. There is no interface between the blob and in the sense of interfacial tension, right? But it behaves like a fluid, a different fluid that is settling. with internal circulations and the particles following these trajectories. But once they reach the end, the velocity of a single particle is slower than the velocity of this suspension. As you pointed out, it settles faster, right? So it leaves out a few particles, and that's why the trailing particles occur, right? Yeah.
Does this happen only for viscous fluids? Like if it was water instead of glycerin, then it's
Good question. So that question is framed in a way that what would happen if I increase the Reynolds number? That is, I decrease the viscous effect, increase the inertial effect, right? And this phenomenon doesn't happen. Something else occurs. What occurs is what you see here. So initially it is like this in the experiment, in the simulation, but as it settles down, the pressure that you will face from here, that pressure exists there too, but it's not strong enough. But in this case, because it's moving with a higher velocity, because the viscosity is smaller, right? The inertia is larger, right? So this will settle faster, meaning a higher Reynolds number. So it has a higher pressure, so it flattens. It becomes like a donut shape, okay? So it forms a donut shape, and then it splits into two. These donut shapes just split, and they re-aggregate, and they form two droplets. One droplet becomes two droplets. And this will continue, this will become a donut again, and it will split again. Right? And this has been documented in the experiment, and using a certain modeling framework for multi-phase flow, we were able to do this. Now, interesting questions for project ideas for this course would be, what would happen if I have a suspension of droplets that are heavy, made of glass beads, and the other one that are light, made of polystyrene, for example, lower density than the liquid. I release the lighter ones from the bottom and the heavier ones from the top. And they're going to go like this. They're going to interact, and the particles will mix, and then they will separate. Right? You don't think so? Why? What do you think will happen?
I think there'll be a force in between them, and it'll be pushed faster. Even the lighter material will be pushed faster. There'll be a
Good. You have good intuition. It might very well happen. When that will happen would be, there is no doubt that every particle, lighter particle, experiences a net upward force. They want to go up. So there must be a greater force for them to be dragging these lighter particles down. Okay. So when would that happen? For example, if the density ratio, I'm putting glass beads with 2.67 and lighter particles with just 0.95, and then water with a density of 1. Then that might happen because these heavy particles have a larger drag. They can carry the liquid with them faster, and so the smaller particles may go with that. Imagine another scenario where I have two particles. One has a density of 1.05, the other one has 0.95, and water is 1. So they are both equally strong in terms of their forces, drag forces. What would happen then? We don't know. Okay? So it's a project some of you may want to take up, and if you find interesting things, it can actually lead to a publication as well. Right? So, but we will learn something about the models that are used to study these interactions between particles. I think we started late, but I should probably stop and time. Can make it some other time. So there are a number of such examples that we are studying in our own lab, trying to understand the fundamentals of multiphase flow interaction. And one phenomenon is if you have two different spheres of glass, two different sizes, one is 200 microns, the other one is 50 microns. You mix them up in a random homogeneous fashion. Put them in a cylindrical vessel and rotate them. Rotate the cylindrical vessel. This kind of devices are used in rotating drums and kilns, for example, in mineral processing, etc. What you find, this was done by a chemical engineer from Northwestern University called Julio Tino. You find that these particles segregate and form beautiful patterns. So the question is, can we have the same modeling framework that we studied for the suspension droplet? Can the same framework work for this one to predict these kinds of behavior? So one set of challenges is trying to identify experiments like these that form spontaneously patterns that are well documented and see whether the same modeling framework can capture different varieties of these phenomena. Here is an example where you have, in fact I should have brought this, next class I will bring it. We have a portable experiment. So this was two thin glasses, and you have glass beads in that in water. Okay, so the glass beads are going to be at the bottom, and I flip that equipment over so that the glass beads are at the top. And then, of course, they are heavy, so they want to settle down. So this kind of a finger that forms in between. Those in petroleum engineering, you know these fingers, right? When you have oil that you are displacing with water, what happens? A fingering instability develops, and you see the same kind of a pattern. There it is between two immiscible liquids. Here it is between a solid in a suspension and a liquid. Okay, this kind of a behavior takes place, and this is the experimental view of what kind of a phenomena occurs. This is simulation-wise. So once again, my goal is to give you a broad exposure to the types of problems, types of challenges. We will go into detail, and we will start putting the algorithms together from the basics, and we will use these algorithms to solve simpler problems. Okay, but today, as I said, it's to give you the big picture, the landscape of what are the challenges and what are the opportunities. So I will upload these slides, and then we will continue from here. Now, Monday is a holiday, I guess, right?
Yes.
So the next lecture will be next Wednesday at the same time. Okay. So if you have ideas on projects, send me an email with a description of it, and otherwise expect a project list to come from me in about a week. By next Wednesday, I'll have them, and I'll put it on Moodle and email you also. And we will do it as a first come first served basis. So if you like the project, one of them, just email me, and I will assign it to you. Okay. All right.
Because I don't have it.
Oh, you don't have it?
No, I added this course this morning because I had the
Oh,
wrong section.
yeah, I can add. Maybe we can do it like now.
I can email you and remind you.
Okay, send me your ID.
Yeah.